Hello, Calculus 6.5. So there's a companion notes paper you should have already about this that has some of the things written down. I still rewrote some on the board, but I didn't rewrite it all because it's already there for you. But there's in this section a thing called the Law of Exponential Change, and I rewrote that up on the board because that's probably like a card-worthy kind of equation. There's two kinds of problems in this. There's growth problems. It's going to happen when this power is more than 0 or positive, in other words. There's decay problems where this would be a negative number. This is going to be measuring like population growths or different things. But if something's increasing, it'll have a positive power. Decreasing is going to have a negative power. Alternative way to use this equation that's sometimes helpful, and this is off in the margin, sometimes they won't tell you enough numbers to work this equation, but they'll have a percentage of things that are remaining, like some stuff disappeared, there's 80% left. If they tell you a percentage, a better way to set this up is percentage left. If you make it a decimal, always turn percents into decimal, equals e to the kt. In these stories, the t is always a time, could be days, weeks, months, years. We just need to make sure we use the same unit consistently through the problem, so you can't mismatch days and years within the same problem. The k is going to be basically a number that every problem is going to be different, and our job is going to be first usually to figure out what that k is so we can do something with it. But every problem will have a different k that we have to do some algebra to solve. The e is just the e that we've been doing. E's kill ln's, ln's kill e's, that's still alive in this. This yo will always be the original amount or the starting amount of something that we're measuring, be it a population or be it something else. The y is going to be some other count of how much we have of something later or now or somewhere down the road. So like, if right now there's 150 people that go to CCA, and someday maybe there's 160 instead. The 150 is this, the 160 is this. Or if I told you, like once upon a time, CCA had 130 people, and now there's 150. This is the 130 from the start. This would be the 150 for down the line. That's how those numbers are working. So in the math book, there's an example, number 1, that I always run through. That's I'm on page 380. It says they're doing a disease eradication, which is kind of timely for our present coronavirus life right now. We wish we could eradicate that disease. But they say, suppose in any given year, so they just gave us a time there of 1. They talked about 1 year. In any given year, the cases worldwide is reduced by 20%. There's 10,000 cases right now, and we want to predict how long it's going to take for the cases to go down to 1,000. And you can probably understand, there's like people doing that right now with this very disease. So this is sort of a timely example in a sense, I guess. Sometimes you read these stories and you're like, who would ever use that? People are using this. At present, if it's following this pattern. So the first thing we do, we want to use the numbers that we know to try to figure out this k. We don't know the k, we want to figure out the k. They didn't tell us what the disease started from. Okay? I'm not going to use this variation of the problem right now. Actually, they did tell us, didn't they? 10,000? Okay. But this is a better equation to use if you can use it. If they drop you a percentage, look to use this. So what they told us is that every year, so the time there is a 1. So 1 year, time of 1. K is a mystery, E is E. The percentage that would be left if they're reducing the cases year by year by 20%. That means 80% of the cases are left. Start with 100 now, 100% now, reduce by 20%, you have 80% of the disease later. If 80% is a decimal, we'd be looking at that. And then do math. So we'd like to solve for k. So to kill an e, do an ln. To get the k completely alone, we would divide by that number. But in this case, that's pretty worthless to divide by 1, but in another question, maybe that's a time other than 1. If you punch this into your calculator, we would know that the K is somewhere in a neighborhood of a number that they don't write down in the example and I didn't write down on my notes because it didn't matter. But punch in ln of 0.8, it's on your screen. For the purposes of this problem, you might want to use the store key a lot because we're going to reuse that K that's on your screen. I'll take a walk, grab my calculator, and just verify it for you. But to store that would be maybe a good idea. So I'm going ln 0.8. It's showing me a negative 0.223 fills my screen. It's not surprising that it's negative because it's a decay problem. They're reducing the disease. So negative powers for reducing things. I'm going to hit the store button and go green button for alphabet K, and it's stored for when I need it later. That'll be the first step in most of these problems. Do some algebra to figure out a K for that problem only. Now we can answer a question. They want us to play a game now where there's 10,000 cases, we reduce it to 1,000, and they want to know how long that's going to take. So that's going to use this equation. There are 10,000 cases to start our story. We want 1,000 cases later. E, K is now known. T is what we don't know. This K that we stored, we know it, and we have it. So we're trying to get this T. To get the T alone, first you'd have to divide by the 10,000, and 0.1 would show on your screen. Then we'd get rid of the E with an ln, and something else would be on your screen. Then we'd have to divide by the K that we stored. So if we grab our calculator and do ln of 0.1, close the parentheses off that they force on us, divide by the K that we stored, and it's going to take 10.3 years, roughly. And the book agrees with that. So on to the next one. On the notes, there's a formula for interest. It says compounded interest. You only need that formula if you care about banking and such. Okay, this is not a formula we're going to use, but that's a real-world formula that I'll just spare you the explanation right now because I know you two are not really super into banking and such. We won't need that. What we are going to need is an interest formula about interest being compounded continuously, which banks don't do this. This is just strictly a calculus kind of fantasy time idea that people just played with and created some problems. But no bank compounds interest continuously. That's not a thing. You get paid your interest maybe every month, maybe every year, maybe every day, depending on your investment at your bank or wherever you are. But there's no one compounding interest continuously. But they make up some what-if theoretical questions just to do calculus with them. So to do that, on these problems, the K is the interest rate, and that's going to be a percentage, again, that we're going to make into a decimal, and that's on the notes. But the example 2, it says, suppose you put $621 in the bank. The 621 lives there. Your starter number in this, the O stands for like original, or a 0 to initiate, like be the initial starting point. But 621 is what you're starting from. We have an E. We have, on this story, an interest rate of 6%, so it's 0.06. And they tell us a time of 8. We're just going to put the money in for 8 years and just let it go. And what they want to know is how much money later. So the variable is there, which is ideal. It's already a loan. So you would just have to punch that in. 621 times, to do an E, it's second, and ln is the E button. And in parentheses, 0.06 times 8, and hit it, you'd have $1,003, and we want to go 0.58 for the 58 cents. Then there's 2 more equations that I put here on the board. Radioactive decay. It's the same equation we were using a minute ago when we started with disease eradication, okay, but it has a negative power guaranteed for decay. And then there's two side equations that make decay easier to obtain. This T, this capital T, is going to refer to a thing called a half-life. The half-life you can find by taking ln of 2 and dividing the k if you know the k. Or you can find decay if you do ln of 2 divided by the half-life if you know the half-life. Here's an explanation of half-life. My chalk is not radioactive, fortunately. That would be bad for my health. Okay? But if my chalk were radioactive, it would mean it would just sort of decay into other things and not be there. So if the half-life of chalk were 10 minutes, at present, if I had that much chalk, if I came back in 10 minutes, I'd probably have that much chalk because it would cut in half. If I came back in 10 minutes again later, this would turn into something like this that you can now probably barely see on the video. And 10 minutes later, this would turn into half as much. There'd always be some there, but it would always cut in half. Radioactive things decay that way, and they measure that decay based on this thing called a half-life. So if I had something with a half-life of 1 day, and every day I come to school to check on my radioactive thing, if I had today 48 pounds of it, tomorrow I'd have 24, and then after that 12, and then 6, and then 3, and then 1.5, and it would keep cutting in half. That's what the half-life is measuring. So I'm looking now at example 4, says polonium-210. Polonium-210, they already wrote the equation for us. When they wrote the example, crash, burn the chalk, it decayed, I guess. When they wrote the equation for us on this example 4, they filled in K's position. The K is 4.95 times 10 to the negative 3. So if they tell you the K, they're asking us in this example to find the half-life. We can just work this equation. This equation is made to find you the half-life. You would just have to punch in the ln of 2, close the parentheses when you punch, divided by that number. And it should shoot you out something in the neighborhood of 140 days. Side application of this is a thing called carbon dating. Someday I'll explain to you carbon dating. Usually at this point, we end up with a big carbon dating explanation. I go off on a rant about evolution and all sorts of things, but I'll save that rant for in person some other day. If you want to, I would ask you, read the box on page 383 about carbon dating and see if you can spot any flaws in their plan. And if you can't, I'll explain to you a whole bunch of flaws in the plan, but we'll save that for another day. But for this, we'll just sort of do the carbon dating the way they wanted, even though I don't particularly buy into this as the most accurate scheme in the universe. It says people who do carbon-14 dating use a half-life of 5,700 years for their work. So they're giving us a half-life for this. So we can figure out the K by doing ln of 2 divided by the half-life. And I would look to store that in your calculator. You might want to store that somewhere more permanent than K. If you go through the homework storing everything in K, that's fine. But anything that has to do with a carbon problem, we're going to use this number. So it doesn't necessarily pay off time-wise to punch in ln of 2 divided by 5,700, ln of 2 divided by 5,700 every time you do one of these problems. So maybe you want to store that in a letter like R for carbon, has an R sound in the middle. I wouldn't put it in C because your quadratic program uses A, B, and C. It might replace it. Like there are other letters we've used that they could get replaced. but I don't think we've ever used R in programming. So if you want to store that in a letter to have it once and for all, that's not a bad idea. But they want us to predict what's the age of something that has 10% of its stuff decayed. Well, I'm going to go back to our percentage equation from way back here. Anytime there's a percentage, use the percentage that's left to equal e to the kt. So in this story, they say 10% of this stuff decayed, so that means 90% remains. So we'd go 0.90, or 0.9 if you prefer, equals e to the negative kt, where k is known. K is what we just stored when we did ln of 2 divided by 5700. If we're trying to use this to figure out a time, and carbon dating problems will always figure out a time, we'd want to kill the e by doing an ln of 0.90. And if e is gone, we just have to divide by the negative of k, because we knew the k and we had stored the k and we know it. And if you punch that in, it says it's 866 years. And I might buy that. I would buy into things that are after the flood. Anything that's before the flood, I don't think I'd be buying those times for reasons that I'll explain in a rant some other time. Those are the ideas in the equations. You usually use an equation to get a k. There will be enough information to get a k for a particular story. And then you'll use that k usually to make a different kind of prediction. But as you probably well know from your word problem experience, there's always variety here. And the only way I could do like a full example of all 20 problems is to do 20 examples, and that's just not always practical. Some of these are going to be really easy, matching exactly to something I did. Some of them are going to be a little more involved. I'd always encourage you to kind of skip around. If you get one that's hard, skip around. But syllabus has homework numbers on it, and I'll talk to you soon.